Hello and welcome to this module on optical communications. In the previous module we have talked about photodetectors in the last two modules. In this module we will talk about remaining aspects of a photodetector. Two are quite important: the response time of a photodetector, because that determines what would be the maximum rate at which one can transmit signals, because if you overcome the transmitter rise time, if you minimize the fiber rise time by appropriately performing the dispersion management, then the last thing that is remaining which limits the bit rate of the communication system is the receiver rise time. And we have talked about it in the last module, saying that it is necessary to reduce this the response time of the APD, which means that one has to try and make the bandwidth of the, not just the APD, for both pin detectors as well as the APD detectors, one has to make the bandwidth to be very large. Okay. So, bandwidth is inversely proportional to the response time of the photodiodes. So, what exactly limits this photodiode response time? Why we cannot have communication, why we cannot have bandwidths which are, say, terahertz or maybe even more than that? We will see the reason why it will be so. As just a small point which I would like to make here, the primary response time limitation comes from the holes, and it is kind of not possible for me to cover that one in this course at this point, as to tell you why the holes are the ones which are moving at a slower velocity compared to the electrons. Okay. So, we will take this fact that holes move, even if both the electric fields applied to the electrons and holes are the same, the mobility of the holes is actually smaller, and therefore holes move at a slower speed compared to that of the electrons. So, electrons move fast, but for the complete current to flow through the circuit, you have to also wait until all the holes are collected in the region, right. So, it is essentially this hole velocity, the fact that hole mobility is smaller compared to the electron mobility in the photodiodes, which essentially limits the response time of the detectors. Okay. In addition to response time, which you would like to minimize it as much as possible, you also want to minimize the noise in the photodetectors. Now, photodetectors are not nice ideal components which will just take optical energy and convert that into electrical energy. They will also contribute a good amount of noise. Some of the noise comes from the photodiode structure itself. The way you have constructed a photodetector, that structure itself will contribute to some noise. Okay. Then thermal agitations inside the material, which will cause a little bit of juggling up and down of the electrons and the holes, constituting a small amount of leakage current, will also contribute to the noise process. In addition to all this, the fundamental noise limitation comes from the fact that the conversion of photons into electrons, right, is not a very deterministic parameter or deterministic process. There is actually it is actually a stochastic process, in the sense that you can imagine someone taking a bullet and then firing at you. Okay. So, someone is firing at you, and if you can kind of put up a metal box or something to collect, you can hear this sound, right. So, one bullet comes in, there will be a sound of ting, one more bullet ting, one more bullet ting. Sometimes you will have multiple bullets come in at a particular time, there will be ting ting ting. So, this kind of a shot, the phenomenon which kind of resembles this shot of a bullet is called as shot noise, and this comes from the fact that electrons which are generated, electron hole pairs which are generated, they are these discrete carriers, and they do not constitute a continuous current flow. Actually, current flows in the form of these bullets. Electrons go in the form of a bullet. Sometimes you get one bullet, sometimes you get two bullets, sometimes you get three, sometimes you get 10, sometimes you get 100. But regardless of whatever that one, it is actually a statistical process. So, there is always a fluctuation about the photo current, which will lead to certain amount of noise. Interestingly, this short noise, we will discuss it slightly later, but here is a summary of this, what happens with a short noise. Short noise unfortunately does not reduce with the increasing optical power. You might think that, well, increasing the optical power should kind of reduce the short noise, but unfortunately the opposite happens, because increased optical power gives rise to a larger photon, the photo carriers, and these photo carriers will amplify the noise associated with them. So, this short noise limitation is not something that would decrease with increasing photodiode. So, you can see that this is kind of counterintuitive, right. So, we will talk about that noise as well. Let us first look at the response time. Okay. We have seen the structure of a PIN diode, right. So, you can assume that this is the P region, and then there is this large pi or the intrinsic region, and then you have the N region. Of course, their dopant profiles have to be chosen appropriately such that much of the photons, maybe if the photons are incident from the N side, then much of the photons will be absorbed only in the intrinsic region. How can we ensure that? We take the material band gaps or materials of different band gaps for the P and N type regions and a different material for the pi or the intrinsic region, right. This is what we called as hetero structures, right. So, if you take this as the indium phosphate, and then if you take this one as the in gas material, then these N and P type regions in the pin photodetector will be transparent to the light at 1550 nanometer. Anything more or less around the conventional band of our optical communication, these two regions will be transparent, and it is the intrinsic region which absorbs the light. Now, look at what happens. Once you have an electron and a hole pair released as a result of absorption of a photon, then there is also an inbuilt electric field, correct. So, there is also an inbuilt electric field which, if you remember, went something like this, right, and then went back to 0. I am exaggerating the electric field out there, but this is how more or less you saw the electric field across the PIN junction, correct. And we assume that the reverse bias which we have applied to this diode is sufficiently large, so that the electric field here is sufficiently strong, okay. And because this electric field, the strongness comes mainly because of this E max thing. For the pin diode, you simply have a maximum electric field, and from there it will reach down to the minimum value, right. So, this is how you would actually see the electric field which has gone to 0 at these 2 points. The field which I had just drawn, if you remember, it was for the APD diodes, because there is a N plus and a P region, that is the multiplication region associated before the intrinsic absorption region, correct. So, the point to note here is that you have a strong electric field which will then separate this positive and negative charges, okay. So, these charges will travel in the opposite direction and they will be collected in the appropriate regions, okay. So, maybe I think this should be the other way around, because electric field is increasing this way. So, it is the holes which have to move this way and the electrons which have to move that other way around, regardless of the fact that they will simply go in the opposite directions. Let us not bother about where they go. What you have to observe here is very interesting. This region wherein the intrinsic region is there, much of the current happens because of the phenomenon called as drift, okay. There is a drift velocity which is related to the mobility. So, if VDE stands for the drift velocity of the electrons and mu E stands for the mobility of the electrons, then this VDE is directly proportional to this mobility times electric field, which is where the field experienced by the electron is. Similarly, if you change this VD into VDH, VDE into VDH, you will get the whole thing. And as I said, whole mobility is less than the electron mobility. Therefore, the speed at which these two photocarriers, electrons and holes, travel will also be different. Now, you might ask why there is a speed problem at all. Well, the current in the intrinsic region is mostly drift, right. But once they come into this majority carrier regions, okay, what would be the main current component here? The main current component has to be diffusion, right. They have come up to here, but the concentration of electrons in this region is much larger. So, if they have to contribute to current, they have to diffuse into this other layer, not the electrons, the holes actually. So, the holes have to diffuse into the N region, the electrons have to diffuse into the P region, so that you are going to get a current, okay. So, this diffusion currents are the ones which you will see at the material interfaces, at the P and I interface and I and N interfaces, you will see this diffusion current, okay. And diffusion is characterized by diffusion constants dP and dN. dP stands for diffusion constant for a p type or a hole, and dN stands for diffusion constant for a electron, okay. So, we are of course not going to look into the full details of this derivation, but I will just briefly motivate you to what is happening. What would be the transit time taken by these electrons and holes? What would be the transit time? you look at what happens. Suppose the generation of these electrons are happening at this edge, right, electron hole pairs are getting generated here, then one of these carriers has to go all the way through the intrinsic region of width Wi, correct. It has to go all the way to that one. What time would it take in order to reach to the end? It would be whatever the width divided by your velocity, right. So, that would be the drift velocity. On the other hand, if generation happens here, I mean for some miraculous reason, the electron hole pairs are generated at this interface, then again there is a travelling of Wi length in order to obtain, in order for it to be collected onto the other region. So, it is this fact that transit time is inversely proportional to Vd, which causes the transit time to be larger for the holes compared to the transit time for the electrons, okay. And bandwidth or the response time, so this would be the response time, bandwidth being the roughly the inverse of this transit time. You see that this is almost limited mainly because of this hole person, right. So, bandwidth gets reduced because of this reason, okay. This can be observed in practice if you take PIN photodiode, okay. So, you take a photodiode, you reverse bias this one appropriately and then send in an optical signal, shine light on it. How do you shine light on it? So, you can shine light on it by focusing light onto that, but what I was interested is to see what kind of change that you have to apply in the optical power. So, if I somehow am able to apply this step optical input, then what happens is that the output photocurrent, right, the photocurrent actually does not go like that, but rather it takes a this kind of a response, okay. In fact, you can see that initially there will be a fast response, then there will be a slow response, okay. I might not have been succeeding to write those responses clearly to show you, maybe the fast response is the one which takes you up to 50% of the final value, and then there is a slow process which takes over, okay. So, this fast process is because of the drift components, they have been generated, they have reached, but now the diffusion time becomes larger, okay. Depending on the doping concentration, the diffusion time will become larger. So, it is effectively the diffusion which limits, okay, the total rise time of your photodiode. Again, when I say this is fast, I am only implying that this is fast with respect to the diffusion process, okay. It is not that this is infinitely fast, that the moment your electron hole pairs are generated, they would have reached the other end, okay. So, this fast process is mainly due to the drift process, and the slow response is mainly because of the diffusion. So, you can see that even if you make Wi smaller, that is reduce the drift time, right, you still will not succeed unless you bring down the diffusion time, right. So, you have to bring down the diffusion time in order to make the overall response reach as fast as possible. The other way to understand this one is that a reversed biased junction, okay, which is essentially the depletion layer that we have here for the I type material, this depletion layer actually is associated with a certain junction capacitance, right, or it is associated with a certain capacitance, right. This capacitance of course is a function of the reverse bias voltage, and in fact reduces when you increase the reverse bias voltage. This is one of the reasons why you want to include a very high reverse bias voltage. So, bias it at a very high reverse bias voltage, your junction capacitance reduces, okay. There will also be some amount of conductivity of the material in the I region. I am talking only of the I region response here. So, there will be some conductivity or equivalently some resistivity rho, right. Resistivity rho, depending on the semiconductor bar, the width and the geometry of that one, will give rise to some amount of resistance R, right. So, even if your external resistance RL were to be made infinite, right, so that it is not loading the photodetector, not exactly in this configuration, but in the op amp TIA configuration, which we will discuss later. Even if you make that part not depend on anything, your fundamental limit again comes from the transit time, which is again basically because of the capacitance, because the transit time is essentially how you are taking the semiconductor I region and then charging the I region, right. So, you cannot just bypass that capacitance that is sitting there. So, put all these things together, the response time of a photodiode is determined by all these characteristics. in most circuit applications it turns out that RL is sufficiently the one which determines the RL, and the junction capacitance Cj is the one which determines the bandwidth of the photodiode. Okay, so one can write this as 1 by bandwidth, and clearly this RL into Cj is the response time of the photodiode. Okay. A thorough analysis of all this requires us to write down the diffusion currents, requires us to write down the drift currents, solve the equations using certain boundary conditions, which is all in my opinion little more complicated than that is sufficient for our course. So, we are not going to look at that one in this course, rather we will move on to considering an important aspect of the photodiode, namely the noise in the photodiode. Okay. Now, how do you define noise? The most common answer that I get when I ask a question, how do you define noise, is that noise is an unwanted signal. It is not a very good definition of noise, because nothing is unwanted. The device does not discriminate whether you are supplying it with a signal or whether there is just noise. As far as the device is concerned, noise photons or the noise electron hole pairs are just as legitimate as your signal photons. Okay. So, there is no difference between a noise and a signal, and this simplistic statement which many people answer when you ask for what is a noise is kind of misleading. What you have to say instead is that noise is a stochastic process which you can characterize only by its averages, statistical averages, and in a signal bandwidth of interest. Of course, you have a signal which you have transmitted. In that bandwidth of interest, it is that stochastic process which corrupts your signal, because it is that noise, I mean it is that part of the signal which is unpredictable, can predictable only in the sense of statistical averages, and it is something that would sit right in the band of your signal interest. To see what I actually mean by this is that to see that one, you consider modulating your optical signal. So, you are sending out some information, you have modulated it. You can take a look at the power spectral density of the modulated waveform. Okay. We will talk about power spectral density slightly later in connection with photodiode noise as well, but you can also define power spectral density for your input signal as well. Okay. So, you define the power spectral density, you see that it is essentially a shape of the Fourier transform, or at least related to the shape of the Fourier transform, and then this power spectral density passes through the channel. At the receiver you are looking at what is the incoming power spectral density, correct. So, because this is optical power we are talking about, there is an optical power density, then there is a broad band. This is one of the other characteristics of the noise. Okay. Most noise of course is broad band, much more broader in its bandwidth compared to the signal, okay, and signal bandwidth. Now, you can try and eliminate all those noise which is not in your receiver band pass filter. You put the receiver a nice band pass filter, so that you let in only the desired signal, that is what you would think, right. So, only that particular signal component within this bandwidth is coming in. Of course, in that bandwidth you actually find two outputs, or rather two components of the output. One component will be the desired signal that you have transmitted, right. So, it is essentially the signal that is riding, which you expect to extract and read the message, or extract the data out there. But each of those values at every time within that bandwidth of that one, that value will have a fluctuation about its, there will be a fluctuation about its mean value. So, this fluctuation, which is characterized only by the statistical averages, is the one that constitutes noise. So, the proper way, or mostly the engineering way of characterizing noise, is to actually talk about the noise spectral density. Okay. We say noise spectral density, and we connect that noise spectral density to another term called as correlation. Okay. Suppose I consider a stochastic process x of t. What a stochastic process means is that if you take a certain time and then measure a quantity, so let us call this quantity as x, okay, then you will see a waveform that would look like this. Each of these sample values is a random variable. You cannot specify, once you have sampled this value, say at some t equal to ti, you have sampled it, you cannot tell us what would be the value of this process x of t at ti plus 1, that is at the next sampling instant. Okay. Of course, it can be continuous, I am just showing you the idea in terms of the discrete ones. So, I cannot tell you what exactly Ti plus 1 is. Suppose this amplitude is 3.4, I cannot tell you what the amplitude here at Ti plus 1 will be with 100% certainty. Rather, I can tell you that there is essentially a probability distribution of the values. Okay. Suppose the probability distribution is centered at 0, which means that most likely next time you are going to get a 0 volt, assuming that this is a noise voltage which we are measuring, you will going to get 0 volt. Okay. Of course, someone else might say no, you won't get 0 volt, but you might also get minus infinity, or maybe this side is a minus infinity, or someone will say no, you will actually get plus infinity. What differentiates between these three statements is what is the likelihood of each of those statements being true, right, and that likelihood is essentially determined by the probability distribution function. So, a stochastic process is essentially a sequence of random variables. These random variables actually follow a certain probability distribution function. Okay. The characteristic of this stochastic process is that you can actually talk about what is the average value of x of t. Okay. So, there is a certain average value which you can talk about. Then you can also introduce what is called as the autocorrelation. You can actually write down this autocorrelation, typically denoted as Rxx of tau, okay, or sometimes a shorter version called Rx of tau. If you are talking about two different random processes or two different random variables, you can talk about Rxy or Ryx. There are certain properties associated with that which makes that these two are essentially symmetric. By the way, these random processes can be complex. It does not mean that there are complex random variables occurring in nature. It simply means that you can think of this complex random process as something that has in-phase and quadrature component. Okay, just as you would think of a signal, modulated signal envelope as something that has a in-phase and a quadrature component. Remember that analytical representation of the signal that we talked about, S plus of t, the Hilbert transform, the up converter, down converter, this is exactly coming from that. Okay. So, noise also can be characterized as having in-phase and quadrature components, and it will separately add to the in-phase component of the signal and add to the other the quadrature phase component of the signal. Okay. And the point is that these two, which together this random process, is something that would actually fall within the bandwidth of the signal. There is no way you can eliminate them. There is no way you can eliminate it. You just have to live with it. Okay. How do you live with it? You expect or you want the system designer to ensure that whatever you receive, that is mostly signal with very little amount of noise. Okay. So, that ratio of mostly signal to less amount of noise is quantified by signal to noise ratio. You want the signal to noise ratio to be as high as possible. Okay. So, coming back to this autocorrelation can be defined as you take the two sample values, one at t and one at say t plus tau, where tau is called as the lag of the autocorrelation, and then find the average value of this. Okay. So, this is what this brackets which I am drawing is the average value or the statistical average value, and this will tell you the autocorrelation. But this is something that is done in the time domain, right. So, this is done in the time domain, but power spectral density, as its name would suggest, is a quantity that is defined in the frequency domain. So, how can I define that one? Well, power spectral density is basically the Fourier transform of this Rxx of tau. Okay. So, you compute the autocorrelation of the process and then take the Fourier transform of that, then you will get the power spectral density. But in addition to this one, there is also another quantity that we normally use. This sigma square is called as the mean square value of the signal. Okay. Mean square value for a process is basically given as the average of x square of t minus the average value square. Okay. Actually, this is coming from average of x of t minus average of x of t itself. So, it is like the deviation from the mean, and then you are taking the square of that deviation. Okay. So, in case where the average of x of t, that is is equal to 0, that is the process has 0 mean as what we would call, then standard deviation will be exactly equal to this quantity sigma square, or standard deviation square will be equal to sigma square, and this sigma square is called as the variance of the process. Okay. Variance is in some sense the power of the process. Variance will actually tell you the power, because it is actually from the Fourier transform relationships you can show that the sigma square is actually given by the power spectral density integrated over the bandwidth. So, if you are looking at a low pass bandwidth, then this would be the power spectral density. Of course, if you are looking for an infinite case, then that would be the total power that is contained inside the sigma square, right. So, it would actually be the power spectral density over the entire band from minus infinity to plus infinity. Okay. Now, why is the sigma square important? Well, we define the signal to noise ratio as the average signal power to noise variance. Okay. Both measured with respect to say 1 ohm resistor, that is to say you assume that the signal is actually dissipating some power in a resistor. Okay. For simplicity we take this resistor to be 1 ohm, and noise variance again is the power of the noise inside that 1 ohm resistor. Okay. This would be the total noise variance inside the bandwidth that you are looking at. Okay. So, you have to be very careful. If I change the bandwidth, then signal to noise ratio will change. Okay. Right. So, if I increase this one, the noise variance will increase. So, I have to be little careful as to what I am actually doing over here. This is for a same bandwidth. Okay. So, that is essentially the signal to noise ratio. Now, what kind of noise can you expect in photodiodes? Okay. You will see that there are two, again the photodiode noise is also expressed in terms of its variance and everything. So, you see that there are many noise processes. One is called as the surface or the leakage dark current, sometimes called as the bulk, and so in addition to this there will also be a bulk dark current. Okay. Together you call this simply as ID. ID will be a dark current noise, that is even when my photodiode is not illuminated, I still get some photocurrent ID of t. This ID of t will have a certain average value plus a variation. Okay. It will be a average value, on top of it, it would be like this varying. Okay. This average value is ID bar and this variation is delta ID of t. So, if you look at the mean of this ID of t process, this is now a stochastic process, the mean of this process is ID itself. The mean of this delta ID of t is 0 because you have simply extracted that average quantity out. Okay. So, this is one noise component, but as I said, the important noise component is the so called short noise. Okay. The short noise variance, let us call this as sigma sh square. This short noise variance is actually very interesting. It is given by 2qiph bar times delta f, where delta f is the bandwidth over which you are integrating the whole thing. Okay. So, this is the short noise variance. Of course, the variance of this delta ID of t process, right, the dark current process is also given by 2q ID bar into delta f. Okay. Delta f being the bandwidth over which you are looking for noise processes. Okay. So, these are the two main noise processes that you get in the photodiodes, but when you put a photodiode inside a circuit in the form of a TIA or a simple load resistor circuit, the load resistor RL will also give rise to an additional noise which is called as thermal noise. Many earlier generation photodiode circuits were limited mainly by the thermal noise of the circuit. Okay. Thermal noise current has a variance, the thermal noise current has a variance of 4 kT by RL into delta F. So, you can see that this variance actually reduces as the value of RL increases. So, these are the two noise processes that you will find in the optical receivers. We will talk about how to optimize the optical receiver in the next class. Thank you very much.